Okay, can we continue? Just to remind you, one fault tolerant is the ideal situation for everything. So everybody would like to have 2 reflectors, 2 electronic boxes, not only in the structural domain, but in any domain. But it's impractical, and of course, it is not possible in most cases. But still, sometimes is the only solution. Okay, about the standard on fatigue and fracture control, just to mention you that fracture control and fatigue is extremely important for the safety, the reliability, for man and unmanned application. This is what we call the structural integrity, is guaranteed with that. Now, just let me tell you a difference between fatigue and fracture. If I do a test where I subject a structure to a cycling set of stresses, I can have the structure, for example, lasting a few million of cycles, 2 million, 3 million of cycles. This is what we call fatigue limit. Of course, if I increase the stress, the number of cycles will decrease. But out of these 2 million of cycles, 1,950,000 are the times that it gets, because of the cycling, to a defect to start. And the last 50,000 is the time that it gets this defect to reach a critical size, and then I have the failure. Okay? So the first 1,950,000 cycles is what is called fatigue. The last 50,000 is what is called crack growth. Then when I do a fracture control, a crack growth design, I assume my defect is already there, which is conservative, okay? Also, you should consider that in space, except for applications like a cryocooler that I mentioned, you have many years of application, the loading of a structure is not like the one of a spacecraft, where you have many lift-off and landings, and you have a lot of loading which is applied during many cycles. In a spacecraft, the loading has less cycles. I don't think that you can talk about, depending on the frequency of a particular element, that you can talk more than 50, 100,000 cycles, with significance for this breakage. Of course, you have also the thermoelastic effect during the whole life of the spacecraft, but this is normally not imposing a huge stress level. It's more related, as I mentioned before, to alignment capabilities, etc. So why do we do that then? Because if you have a problem with an aircraft, for example, with a car, you can solve the problem here on ground. When we launch our spacecraft, unless it is a manned space flight, and also costs a lot of money, for an unmanned spacecraft you cannot repair anything. That's why for critical elements we apply this damage tolerance approach. Okay. This chart talks about how it is implemented, the fatigue analysis as part of the fracture control. And I say sometimes we do fatigue analysis, sometimes we do crack growth analysis, depending on the criticality of the element. And this is the software that is available. It's a software that is provided by ESA to all companies working in a space. The ESA load and the NASGRO are 2 modules which are the ESA load is implementing the load, performing or calculating the load spectrum depending on the number of load events and the frequency of the payload. The NASGRO is a module developed by NASA, is calculating the increase of the crack up to the location, and all this is implemented in the ESA crack. Okay, just for you to know that this is available, and the industry also has access to this, only for the space applications. Let's go now to the big part of the development of the spacecraft called verification. We have three types of verifications: by analysis, by test, and by commonality. The first thing we have to distinguish is the model philosophy that I mentioned before. We have a prototype approach where I have a qualification model which is tested at higher levels than the flight levels, and then the flight model is tested to the acceptance levels, which are the flight levels. I have the proto-flight approach where my model is tested to the high levels, with some exceptions, and two durations which are acceptance. But the proto-flight levels are the same than the qualification levels. And then I have something called STM, Structure Thermal Model, which is applicable to both prototype and proto-flight. I'm telling you that when I started to work in this agency, the prototype approach was the typical one, including an STM. So we have STM, qual model, flight model. With the passing the years, we had only the proto-flight, most cases, with an STM. And today we have proto-flight without STM because of cost reductions. And because I think there is also a lot of experience, I have to say, which I think is logical. Sometimes when there is a new development, I think we should never announce to have an STM. This is my personal opinion, at least for the structural aspects. But I have to tell you that today there are developments where we have only proto-flight. We don't have even STM. Another important point to prepare the verification is to have verifiable low-level requirements which are flow down from high-level requirements. So one of the most important tasks in the satellite development, spacecraft development is, I mentioned already, the verification. The verification is done, as I showed you in this chart with the V, at different levels. If the requirements are verified at all levels, it's because they have been properly flowed down by the prime. So the job of a prime, which is very important, is twofold, is to identify all the system level requirements and also to be able to flow down those system level requirements into proper requirements of subsystem and unit. And then in terms of structural analysis, structural discipline, we have a typical this is an example, there are many. The typical top-level requirement is that the structure shall support the payload and the spacecraft subsystem with enough strength and stiffness, okay? And then a typical flow-down requirement is that all the inserts, which I have in my design, my subsystem, in my structure, should be verified by test, all the flight inserts. All my margin of safety shall be above 0. Let's go to the one to the right. Today we have, it's very common to have carbon fiber aluminum sandwiches, carbon fiber facings, aluminum honeycomb sandwiches, with a lot of inserts which are potted. Maybe you can have hundreds of those inserts. The requirement calls for the verification of the strength of all those flight inserts. I'm talking about flight hardware, 100%. This is something that is not done in all the developments. Sometimes 100% is verified, sometimes because there is a lot of experience, a lot of values of strength of the insert vis-a-vis the manufacturing process, which is very well known, there is only few of them which are tested. So this is a typical example. The cost of the structure will be different if I have to proof test 100 inserts that if I have to proof test 500 or 50. So this is a good example how important it is to flow down the requirements properly, because this affects the whole development and the verification. Here we have a typical flow chart of how it is performed, the design and the verification of a spacecraft. So we start with the launch vehicle user manual. It's giving you all the constraints. You continue with the structural configuration of your spacecraft. It's not the same spacecraft that is looking to the Earth than a spacecraft that is looking to the stars. No, I think that everybody knows that. It's not the same one spacecraft that goes like Rosetta, very far away from the sun, that another one like Solar Orbiter that is very close to the sun. You have different configurations. You need a thermal shield for the second one. You need big solar panels for the Rosetta, etc. There are differences. And in this configuration, you have to consider what I was saying, these functional requirements for all the subsystems. Then you have a preliminary spacecraft design, and for this you use the launch loads from the user manual of the launcher. And of course, you implement your natural frequency constraints. You do a structure analysis and developing a fine element model, and then which consists of a dynamic analysis, a stress analysis, and you also do a thermoelastic analysis, for which you have to do a thermal analysis first. Then, if you have the thermal analysis is not okay because you have high temperature, high gradients, and high stresses, then you refine the thing. You also do the same thing with the spacecraft dynamic model, and you have a loop where you do an initial couple of analysis with the launcher until you have already designed that works, and then you start manufacturing the spacecraft, and you do all the environmental testing that we have mentioned before. Static test, which is normally done in the STM, modal survey, if it is normally it's not done at spacecraft level anymore. You do the sign test, the random test. Random test is done at subsystem mainly. There is no random test done at spacecraft level. It is done on acoustic. Acoustic test is performed. And then you have also your shock load testing. Okay? Today, in what concerns the verification to the low frequency dynamics that we do with the couple of analysis, there are more and more tools, and in the future, these additional tools will allow that basically the spacecraft developer will be able to do, if they want, one couple of analysis per day. This is something that is still not implemented, but will come in the future. Of course, you don't need to do a couple of analysis per day. What I try to say is that if you get the proper data from the launcher developer, you can do, the spatial developer can do a couple of analysis as frequently as they need to refine the loads and to make the design cycle even, and later on the verification, much easier and much smoother. This is coming. This is still not implemented, and in the current development, what you have is 2 or 3 couple of analyses which are planned in the whole development. But in between, we are designing with very conservative loads, which sometimes give problems because we have a lot of mass, or we have a lot of stiffness, more than we need, etc. Just the idea for you is that for the low frequency dynamics, there is a loop of the design with a couple of analysis which is refining the loads. If this loop can be done directly by the developer without interfacing every time with the launcher developer, that will be faster. And this is something that it was presented for the first time in the structures conference here in Este last year, and it's something that is working. A lot of companies are working and will be developed more and more. Also, we have been talking only about capital analysis. I'm also telling you that these days there are very good tools to perform good predictions of the acoustics loading. So at the end we put the spacecraft, like we put it in the shaker, in the sign test, we also put the spacecraft in the acoustic chamber. But it is possible to reproduce beforehand what we are going to have in the final verification is done by test, but it is possible to do it beforehand by analysis. So we have an idea of whether the acoustic pressure will be okay for all the elements which are critical to acoustic pressure, and we have also idea what will be the random levels in the different small units that we have in our spacecraft. And this is later on confirmed by the final acoustic test. So the design, and this is the message, the design process and the verification process are more and more these days supported by more sophisticated analytical means, which are not eliminating at all the testing, because this I don't think will happen, but will help in having a much easier and much smoother verification, okay? Together with the fact that for the sign test, I also believe that in the next years, we will have a verification that will be done with the direct transients at the interface of the spacecraft and not by this sign sweep that is quite conservative. But this is still to come, the two things. Okay. This is an example of mechanical testing on ground. This is the static test to check the structure of the Sentinel-3. What you have at the left is the primary structure, and this was tested with the device you have on the right, including test jigs and actuator. This was just to prove that we could test that the structure had the capability to withstand all the loads, and this is done at the early stage as soon as we have an STM of the spacecraft. Of course, when I don't have an STM, I cannot do the test, obviously, and I take more risk. This other example is a typical sign. Well, this is not sorry, I made a mistake. This is not a sign test. This is what we call a sign burst. I didn't mention. This is a test which is done at a given frequency and is also equivalent quasi-static test. So if I come back to the chart before, this is a static test where I apply to my structure a number of actuators, and I have to implement a set of test jigs, and then I load my structure with a static load. I can also take my structure, I can put it in a shaker, and instead of sweeping from 5 to 120, I can take it at 10 Hertz, and I do a test at 10 Hertz. Of course, I ramp up first, but then I stay a number of cycles at the 5Gs, for example, and then I go down. And this is a way to implement in my structure 5Gs in a quasi-static way. I do not like this test because it's quite damaging. I think that the static is better, and this is not done very often. A similar version of this setup, we don't have to change, is a typical sign where I sweep from 5 to 100, 120. And this test, which is the sign burst or sign dwell that I mentioned at a given frequency, was, in this case, was 15 Hertz, was done to qualify the structure, also with the STM. Another test that is part of the verification is the acoustic noise test. This is the Rosetta spacecraft in the large acoustic facility of ESTEC. Here, what is important is that I have a sound field that is uniform and is implemented similar to the spectra that is coming from the launcher. And then the chamber is made of has to be large enough because we have a volume effect. I cannot put in an acoustic chamber a spacecraft that is taking 90% of the volume, because then I would not be able to control the sound input. The walls are very thick, but they also have to be smooth to allow high reverberation, which is the effect that will allow me to have a specific sound pressure levels with a given spectrum, so many decibels. Typical decibels are 130, 140 for a qualification test. More than that at mid-frequencies in the order from 300 until 2000 hertz or even less, and then going down afterwards. It's also important to see that when I have a spacecraft in the acoustic chamber, I should try to have the spacecraft not parallel to the walls, because this will also be, you see that Rosetta is a bit rotated. Okay. In the last years, there is another acoustic test method that is being developed that is called the direct field acoustic noise test. And this is basically to surround my spacecraft by a number of loudspeakers and a control. I need a controller. And at this moment, there are a number of spacecraft which are verified with this. For example, Galileo. Some of Galileo's spacecraft were verified by this method. There are a lot of American spacecraft which are verified with this method. And now we are working at ESA in setting up guidelines to compare this with the other method to make sure that we can use both methods to the choice of the prime, and that both are going in the same direction to qualify acoustically your structure. Okay, this one, you have a dedicated facility where you put your spacecraft. Due to the shape of to the volume of the facility, due to the different holes that you can see there, to the smoothness and the thick walls, you are able to provide a reverberant noise field. Okay? Control. So you have the given energy at each frequency. In this one, you can be anywhere. You can be in the living room of your house. Of course, I don't recommend your house. You surround the spacecraft by a number of loudspeakers, and then you need a controller. There are companies which are developing controllers which are controlling the energy in each loudspeaker, and in the end, it is a sound level that is called direct field acoustic, but should be providing the same, and this is the difficult thing what we are evaluating, the same energy at each frequency band. The advantage of the second one, it depends. The bottle is always half empty, half full. With this, you can put your loudspeakers in a truck and you can go and test anywhere. With the other one, you need to have this facility. Yes, but once you have the facility, well, you need this other thing. So it depends who goes to, is the facility that goes to where the spacecraft is, and then I do direct field acoustic, or is the spacecraft that goes to the facility and I do a typical reverberant acoustic test. So the important thing is that both are possible and both are providing the final goal, that is to qualify. One thing I have not mentioned, maybe sorry if I forgot, is that the most important objective of a test is to provide the input. So if I do a sign test and I have to test my spacecraft to 1G up to 40 hertz, and then I go to 5Gs later on, I should be able to control the shaker to provide this input. If I provide more, I can break it. If I provide less, I will underqualify my spacecraft. In acoustic, it's the same thing. If I have a reverberant chamber, because of the experience, I know that I will be able to implement the spectrum. And even before that, there are empty runs which are done in the acoustic before I put my spacecraft there. With the direct field acoustic, I should be able also to implement the input and not to over-test or under-test. So this is the important objective of each test. Of course, if you are responsible, yeah, you have a question.
There is no constraint on the environment in this case. Everywhere, like
Yeah,
really everywhere.
you can do everywhere, yes. What do you mean constrained by the environment?
No closed environment can affect.
No, in this case, no. For example, I don't have details here, but if I'm doing a microvibration test, for example, maybe the air conditioning, because they are very tiny and vibrations, could have an effect. I have to switch them off. In extreme cases, I do the test at night to avoid the effect of the traffic or whatever. But for this, no. For this, there is no specific. Normally, this is done. There was a test done here in ESTEC, and it was done in a pre-integration area. So they came with the truck with all the speakers. They surrounded the test article, and they implemented the test with a controller. There is no constraint, specific constraint for this. Okay. Then I think I already mentioned these two things. We should do the CLAs at least 3 times, hopefully in the future even more. And the shock test should only be performed on the STM to identify this is also part of the verification, of course, on the STM to verify the transfer functions and to do as less shock tests as possible in the flight units. Okay, what is the final verification? The final verification, everybody knows what a VCD is, no? A verification control document. Is when you are already full compliance of all the requirements. If I have requirements, I verify by analysis, I have the stress report, the analysis report. If I have requirements verified by test, I have the test report, and everything is okay. Also, before that, normally there is something that is called the VCD is the final one, but you also have the verification control procedure, where you verify really what do I have to do. You verify, no, I don't like to use the same word. You check whether the verification of your requirements is the appropriate. So sometimes you do a verification of analysis that is not enough, and this you have to know before. For example, I have thrusters in my spacecraft. I may have thrusters for attitude and orbit control. I want to have these thrusters tested at unit level. Some companies say, no, I have a model of my thruster, I don't do any test, I do just an analysis. This is a typical discussion example. Then, before I enter into the full verification, I need to have this clarified. Because if I go to my verification, I request a test on the thrusters, a thruster level, and they have not performed it, and then we have a hole and a big issue. This is the important thing. And then I also have to assess the risk. Sometimes, taking the same example, I don't do a thruster level test because of money, and then I assess the risk. I accept the analysis will be sufficient, but then I have a risk, and this risk I undertake, and then my verification will not have this dedicated test. I know it beforehand, and has been accepted by everybody. Okay? So this is the important thing. The typical criteria for assessing the verification to the loads is that all the margin of safety must be greater or equal to 0. All the structures to be qualified by static or sinusoidal testing, and also by acoustic or random testing. So I think what is written here is obvious. You also know what the margin of safety is. the formula there is the big formula everybody uses. So I have in the upper part, I have the design allowables, loads, stresses, whatever. In the lower part, I have my design limit load that I apply with exact factor safety, and then I divide the values and I rest 1. And if the margin is positive, means that my design allowable is higher than the limit load times the factor safety. Then I also have to do the verification load cycle. And I have the capital analysis or the acoustic analysis, etc., plus the test. And then I have to have the models correlated and the load production. And then I have to have margin of safety which are positive. So basically, when I do, for example, the verification, let's start to the acoustic loading. When I do my acoustic test, I check that all the random levels, which I have in all the internal parts of the structure, are spectra which are lower than the ones the elements are being qualified to. If I have the pressure loads on elements which are sensitive to the acoustic pressure, I also have verified that the structure, whatever reflector, a sun shield, a solar panel, has undertaken these loads by test, or because they have already been done many times, we already know that they will take it, whatever. If I do a capital analysis, I verify that the loads coming from my final capital analysis with the model validated, etc., are below the ones I've used for the design, and that's enough, because my design already have margin of safety which are positive. So this is basically the way it is done. Now, main inconsistencies of the load verification process. I mentioned a number of times in this presentation, in this course, that the sign test is an artificial one. We have uniaxial vibration and shock test facilities. Well, the dynamic environment for the space break of hour are typically multi-axis. We have 6 degrees of freedom system inputs. For the shock, we don't have solution yet. For the sign, I already told you something we are starting. I don't want to repeat, you already know. But what is true is that when we do a sign test, we do one in 3 axes. So the sign test is not only quite damaging because it's sweeping the whole frequency band, but we also do that in the 3 axes, separated, whilst in reality it's happening all in multi-axis. Also, the tests are performed environment by environment, even if they occur simultaneously. Sometimes, because of that, we implement load superposition techniques by analysis. This is not done very often, I have to tell you, but sometimes it is done. If a structure is, for example, sensitive to a particular load cycle where temperature is important, plays an important role. I tell you, in some flights of Vega, for example, we have high temperatures, 120, 150 degrees in certain flight events, because there is a lot of sun, and at the same time, we still have the thrust of one of the stages. Then you have to do your thermal test, you do your capital analysis, and then you combine and see that when you combine the mechanical loads with the thermal load, the margin is still positive. This can happen. And then the last point is the one I already mentioned. Low frequency transient often simulated at the subsystem and system assembly level using a swept sign vibration test. I mentioned many times, mainly because of its simplicity in specification and testing, but it's conservative. Another point that I also mentioned is that we have an infinite mechanical impedance on the shaker. I told you that we have an infinity read interface. When I put my spacecraft in the launcher, it's not so rigid, it's soft. And then this may lead to over-testing. That's why we have to be very careful with the notching. Vibroacoustic environment, this is another inconsistency, often simulated at the subsystem and units assembly level using a random vibration test. This is what I explained before, and this is now less and less a problem, because I can do an analysis at the very beginning, an acoustic analysis, and I can adjust the random levels. And this is later on proved by the acoustic test at the very end in the verification. But I will not use, like we were using before, random level spectra that were very conservative, coming on the envelope of the envelope of the envelope of many missions. And then I don't have to over-test my electronic box to a high-level random spectrum when in the mission is going to see a tenth of it or a fourth of it or whatever. Test levels largely based on computational analysis. For this reason, it is important to validate critical load analysis. This is a fact, but at the same time, we are these days with analysis not only performing the analytical verification, we are also able to simulate the test very well. So we know whether our test is going to be dangerous or not for our hardware, talking mainly about the flight hardware. So this is an inconsistency that is solved, because today nobody's putting a spacecraft in a shaker or in an acoustic if we have not done an analysis to simulate the test before. That is always the case. Okay, now there are a number of charts which are following. So we have finished the mission, the design, and the verification, which were the main topics of the structural requirements. Now we have another elements which are still in the standard called production manufacturing. I will not go in detail, but I also discuss, I have already discussed a number of them. Mainly the one I didn't discuss much in detail was the health and safety, but I think it's obvious that you must have, you can have a lot of problems when you are integrating, manufacturing, assembling your spacecraft on ground, because there are many hazards. The typical one I put before is the pressurized elements, the tanks, and all the propulsion systems of your spacecraft. They are hazardous. You also have hazardous substances which may affect people which are on ground. There are even facilities. I've seen facilities where they do, these days we use a lot of overwrap pressure vessels. It's a pressure vessel made of carbon fiber with a liner inside, either titanium or aluminum. The property of these vessels is that they have a high pressure, very high pressure, 200 bars, and when they fail, they explode. And then I've seen in some cases, they do explosion analysis. And then when you have the production facility of the spacecraft, there is maybe a perimeter of 20 meters where only the people which are dealing with this are allowed to enter, because this minimizes the risk for all the other people which are in the integration facility. So nobody can enter there when there is a pressure built up in the pressure vessel. This is an example of requirements. You can put that requirement in your general system requirement. Or if you are the prime, you can put that requirement to your subsystems and make sure that this will never happen, that nobody except the one or two persons which are working on this pressurized element will be working close to it. In service, you have ground inspections, in-orbit inspections, evaluation of damages, maintenance, and repair. I think we have, maybe repair is something that I have not discussed, but there are a lot of repairs which are done, mainly in composites, It's very typical to have failures in composite because things drop. You don't believe it, but it happens. And then you have to put doublers on your sandwich because you have damaged the spacecraft, the structure. When you do a sandwich made in carbon fiber and you are integrating that, you must have it protected against the impact of tools, etc., that happen during the integration. When this happens, you have to repair. This has been done. Okay, now it is 12 o'clock. I have a set of back charts. We can go through them quickly in the next 10-15 minutes, and then after that we can finish. But this is basically what I wanted to give to you. Just recapping, I'll say that I'm going through all the elements of the table of contents of the Structure General Requirement Standard, and I made reference to the other standards, like materials or fracture control, etc., that are connected to this one. The only standard that I have not mentioned too much is the one on pressurized, because this is a very dedicated one that will need another full course. But I believe it's better for you to give this general view of how we deal with the structures in the development of a spacecraft, and I think it's giving you more insight of the general requirements. Now, going into the back charts, I think I want to go mainly on not to repeat what I already said. I prefer to go through specific pictures. You have all this information, you will get the presentation. This is the typical Vega launch. You have the P80 is the first solid booster. The second one is the Z23. In the couple analysis, we consider the ignition and the blast wave. We also the maximum gust and the maximum acceleration. Then we also have the pressure oscillations. Then, once this one is released, we have the second booster, that is the Z23, for which the load case we consider a couple analysis the ignition, and then pressure oscillations. And then we are left with the last one, the Zafiro 9, for which we only consider ignition. After these three solid boosters, you have the Avon that is liquid driven. It's not solid, and it's the one that is used to locate the spacecraft in a particular configuration or attitude, and also to bring the upper stage down into the sea for demise. Okay, these are things we have already gone through in Ariane 5. The dynamic coupling I already mentioned. Let me go to, this is how we perform what I explained before about the shock response spectrum. So in the left, you have the time domain shock. This time domain transient has a lot of frequency content. And then I have my set of 1 degree of freedom systems, which I'm changing the stiffness and the mass. I'm just sweeping the frequency, and I'm calculating for each one, calculating the response to the transient. And then I get the curve in the right, that is the shock response spectrum. One thing I didn't mention before, but it's obvious, when I do the SRS, I lose the phase information, for sure. But this is the way it works, because doing the verification by analysis is very time consuming in the time domain, and sometimes it's not possible. We have limitations with the step. When you do an integration of this transient in the time domain, you have limitations with the step you can put. And then if the model is too big, it's better to do this, but that's more practical. That's why the SRS is implemented. Okay, this is a typical sign test of Ariane 5 manual. You have the blue one is for the lateral and the red one for the longitudinal. I tell you that from my capital analysis, normally I come to a sign test that is below, for the lateral is below the blue, and for the axial below the red, much below. So these are very, very extreme conditions, because the launcher, of course, wants to be conservative. And these are the levels of the sign excitation at the spectral base. You can go 0.8 and then 0.6. In practice, we put less, for the reason I told you, because I have already made a design with less coupling, and then I have less loads, and then I can have a much lower sign test. Okay. But just to give you an example. Venting, just instead of this text, I think it's better to go, this is the depressurization under the fading. It's an important thing. You see how the pressure is going down. Then, depending on the size of your hole and the amount of volume to be vented, you have a maximum delta P. Of course, if you don't have hole, the maximum delta P will be 1 bar. And 1 bar for a big volume, you can break it. Well, you will break it, most likely. But when you do the holes, when you have to vent, you have enclosed volumes in your spacecraft, you have to consider this. This is a typical pressure decay during the ascent of a launcher. Then the other thing is, you already saw this picture before, is acoustic loads. This is a typical spectrum I was mentioning before. In this case, we go to maximum 133 dBs, and the frequency band is smaller than what I said before, but okay, it depends on the vehicle. Just to give you an idea of the typical spectrum that is applied. Okay, then this is the typical box for random vibration. This, we already have a similar thing where I explained to you all the environment. Let me go, because I want to show you. I didn't say much about microvibration, but this is an important thing. Microvibration is also a driving requirement in 2 directions. You have the emissivity and you have the absorptivity. So if I have a spacecraft and I have a very delicate instrument, then the emissions of the disturbers, which could be the reaction wheels or could be the cryocoolers or any other thing, are very important because they are transmitted through the structure up to my equipment, and then my instrument can be not working properly. So this is one case. The other case is that I have, the other case is that I have 2 instruments, and then one of the instruments is also having a disturber rotating part, for example, and then it is not working if it gets a lot of noise from the other instrument and from the other disturbers. So what I try to say is that microvibration is an effect that you have to consider in the 2 directions. And it's quite demanding. These days, we do a lot of analysis and characterization, and also this microvibration is happening in a very wide frequency band. We can be at low frequencies, 5 Hertz, we can go up to 200-300 Hertz. And the final test is done by hanging the spacecraft and switching it on and measuring on ground. Of course, this is validated with a model where you remove later on the gravity, etc. All these kind of things are done, but there is a lot of characterization and a lot of verification performed on microvibrations. It's an important topic because at the end of the day, it's is part of the functioning of the spacecraft. Okay, these are rotating wheels. A few words on model survey. This is a model survey which was done for Goche long time ago. Basically, what you have is in the left side you have the actual hardware. In the middle you have a finite element model of Goche, and in the right side what you have is what we call the test model. The test model, all the red points are points where you have accelerometers. Then you excite in different locations, and then you recover these measurements, and with these measurements you can extrapolate to the middle FEM, and then you can adjust the FEM to the real modes which you have measured in the right one, and then you have an FEM that is representative of the mode shapes and the frequencies of the structure. Okay, these are examples of vibration tests. I just want to show you a last one, and then I think we can finish. This is IXV, vibration test. This is Herschel-Planck vibration test. This is a chart I like because you have, in the right one, you have the two. You have the photo of the test in the shaker, and in the right one, you have the FEM of everything. Yeah? And then this is what you need to validate your model. And then the last chart I want to show you is, again, on the sign test. And I want to show you because I want to let you know that in the sign vibration test, of course, we input the input at the shaker, but we have not only accelerometers in the whole spacecraft, we also have, and this is very important, a force measurement device at the interface. So I mentioned you before that we do a notching, no? To avoid overtesting. This notching more and more is controlled by the interface forces at the interface between the spacecraft and the shaker. This is called primary notching. There is a secondary notching that is based on accelerations in certain local position of the spacecraft where you have different payloads or reflectors or whatever, and they are based on acceleration. But the most important is the one that is based on interface forces. And what we do is we make sure that I decrease the input. The input of the shaker is always in acceleration. I decrease the input, but I will never go low when I reach the resonance of the spacecraft. I will never go below a value of acceleration at the input that will give me a force at interface that is less than the one that will be seen during the actual flight. Also, for the secondary notching, I will never go to an acceleration that will be less than the one that will be seen by this particular element of the spacecraft. With those two notchings, I can be sure that I will not under-test my payload, my spacecraft, and I will also make sure that the launch authority will approve my test. And this is basically what I have. I think that it's good that this time this year I had the time, because normally I had more charts, many charts, and it was during the years you start learning, you cut them, and I hope that I give you an insight of the whole process, design and verification, functionality of the spacecraft structure. And if you have any question, you can ask now, and if you want, you can ask anytime. You can get my email address and all my data from the course organizers, so no problem. Thanks a lot for your time. Thank you.